The harsh reality of the hunt is a battle of wits, a competition between the brains of predator and prey. To succeed and survive, an animal must understand the environment it lives in. That understanding enters the brain through the senses. Most of all, for many animals, through the eyes. When I was at school, an enthusiastic biology teacher taught me about nerve cells and the impulses that they transmit. I remember wondering then about the mystery of the brain, millions upon millions of those nerve cells. Today, in Oxford, where I work, the fascination still holds. A fascination with the way that our brains can convert impulses into understanding, and how nerve cells can give us knowledge of the world. Like any animal that moves around in the world, we have to plan our actions and control our movements. And to do that, we have to hear, to feel, and to see the world around us. We have to understand the things that are happening and to anticipate what they'll do next. The picture that we have in our mind is only part of the way that we use the information from our eyes. We also use it to coordinate hand and eye, and to recognize people, and to know where we are. And we do all of those things effortlessly. Vision seems the easiest thing in the world. Or is it?
Well, it seems easy. I'm going to shut my eyes, I can't see a blind thing, but open them and there's you. And the fact there's a tree behind you and so on. Amazing. But obviously we know, don't we, that it's an amazingly complex, subtle business that goes on in my head, although it seems easy. It's not like running a mile or a marathon like you do or something. It just all happens just like that. But we know that it's actually complex, difficult processes, so to speak, to understand are going on, because we can't reproduce it in computers. Even the biggest computers in the world can only see very crudely. That either means, surely, that the brain is an enormous computer, bigger than anything we can handle or have from our technology, or that there are a lot of cunning processes going on that we don't yet really understand.
When computer scientists first started to design robots that could move around the world, they had to give them senses too. And as they tried to make artificial vision systems, they realized just how difficult it is to see.
Has turned out to be much harder than anybody thought. I mean, on the one hand, there are so many engineering applications we want to work on, such as navigating mobile vehicles around or inspecting various kinds of industrial artifacts. And yet, right at the earliest stages, we have information flying at us faster than we can handle, like water out of a fire hose.
That gush of information from the eyes pours into an area at the back of the cerebral hemispheres, the visual cortex. Signals from the ear reach another small region, and information from the skin ends up in its own strip of sensory cortex. Somehow the messages from the fire hose of the senses are distilled into decisions that lead to movements, the responsibility of another strip, the motor cortex. These regions of the cortex were discovered by neurologists 100 years ago. But in between was a vast unknown land, a terra incognita that we've now started to explore. as we search for the differences between what brains and computers can do. How can the brain do what no computer has yet achieved? How can my brain calculate the solid shape of this book from the flat image of it inside my eye? In the 17th century, it all seemed so easy to the French philosopher and scientist René Descartes. He'd done experiments on an ox's eyeball that he'd bought from a butcher, and he'd seen the retinal image formed inside it. That little picture of the world seemed to hold the secret of vision. The eye does capture an image of the world in the same way that a camera does. Eyes are optical instruments, but they alone don't see. They simply begin the process of vision, a process that occupies much of the brain. The eyes of each animal are perfectly adapted to its habits and habitat. In most vertebrates, each waking second, the eyes send millions of items of information to the brain. The upside-down image in the human eye falls on a sensitive array of nerve cells that catch the light and convert it into electrical responses. The signals pass through layers of neurons in the retina and head towards the brain along the million fibers of the optic nerve. The fibers from left and right eyes crisscross. After a relay along the way, the signals reach that region of the cerebral hemispheres just under the skull at the back of the head, the primary visual cortex. Each half of the brain receives information about the opposite half of the visual scene. At the University of California at Berkeley, Russell Deverloy and his colleagues set out to find out just how precisely this picture is laid out across the brain. This image was flashed before the eyes of a monkey. Would the visual images be exposed onto the back of the brain, the way images are exposed in a dark room onto photographic paper?
The technique that we used was to give the monkey minute quantities of radioactive sugar, which is taken up by the most active cells in the cortex. Then when we looked at the X-ray picture of the cortex, we could see which cells were most responsive to this pattern. And the amazing thing was the precision of this pattern that we saw in the cortex, where you can see all of the stripes and rings laid out beautifully on the cortical surface. We were really amazed at how precisely the mapping was onto the cortex.
Pictures in the brain? Here we are back at the paradox of René Descartes. Vision can't be just a picture in the brain, because there's no one in there to look at it. To find out how understanding enters the structure of the brain, we must look closer at the billions of individual nerve cells that make up the retina of the eye and the cerebral cortex. When I went to Cambridge as a medical student in 1962, I discovered that dozens of people there were studying vision. Their excitement was infectious, and I too became fascinated with the question of how we see things. I learnt about the work of Horace Barlow, who was working in Cambridge using the new techniques for recording the electrical impulses of single nerve cells and their fibers with tiny microelectrodes. In 1953, when I was just 9, he described the way in which some fibers in the frog's optic nerve respond selectively to movement in the visual scene, some to small black objects about the size of a fly. Barlow interpreted this in terms of the needs of a frog to understand its visual world, and he suggested that vision consists of the detection of important features in the image by individual nerve cells. When I graduated from Cambridge, I had the good fortune to go and work with Horace Barlow, who'd moved to California. I wanted to study the visual part of the cerebral cortex, where messages arrive from the eyes, making that kind of picture in the brain. I, like everyone else who was interested in vision, had been astounded by work done in the United States by David Hubel and Torsten Wiesel. In 1982, they won the Nobel Prize for research that they'd started in the late 50s. They recorded from those neurons of knowledge in the visual cortex, and they discovered what looked like an alphabet in the language of vision.
To start with, the cortex is a plate of cells a couple of millimeters thick and a foot or so in surface area. The part of the cortex that we're dealing with, the primary visual cortex, is a chunk of that, about the size of maybe a credit card. Here is the smooth surface of the primary visual cortex. This is the part that's tucked underneath. And
though it's only 2 millimeters thick, the cortex contains about 100,000 nerve cells under each square millimeter of the surface. Hubel and Wiesel started their work on cats, projecting patterns in front of the eyes of an anesthetized animal, while a tiny electrode picked up signals from cells in the cortex.
When we started working, Torsten and I, in the late 50s, we set up our first experiments, and at the beginning we couldn't make the cells fire at all. We'd shine lights all over the screen, and nothing seemed to work. And rather by accident, one day, we were shining small spots onto the screen, and we found that the black dot seemed to be working in a way that at first we couldn't understand until we found that it was the process of slipping the piece of glass into the projector, which swept a line, a very faint, precise, narrow line across the retina. And every time we did that, we'd get a response. And even more than that, the line produced a response as it swept across the screen in one direction, but not in the reverse direction.
Later, they discovered that these cells that respond to lines at particular angles are arranged with extraordinary regularity within the cortex. When a penetration goes straight down a column of nerve cells, every one that responds specifically to lines and edges prefers the same orientation, an oblique angle, let's say. And in the next penetration, a quarter of a millimeter away, everything responds to a different angle.
Well, what we found one day was in a monkey. We made a penetration obliquely through the cortex, and in the course of going about 1.5 to 2 millimeters, we had a sequence of orientations that was highly ordered, with steps of about 10 degrees from one cell to the next. So as we went down, we had a progressive shift. Every time we pushed the electrode forward, there was a shift. So by the time we were finished, we had gone around the clock several times and seen 58 sequences without a single large jump. And it was very clear at that point that the cortex must be arranged with an enormous degree of order.
My colleagues and I at Cambridge discovered in a very direct way how much this analysis of lines and angles matters to any animal, and how it depends on visual experience early in life. A cat that had been reared in an environment without vertical edges can see a horizontal line, but has difficulty detecting vertical lines. The columns of brain cells responsive to vertical didn't develop properly. Most computer vision systems nowadays use the same principle of detecting edges and lines as the first step in recognizing shapes. Computer science has learnt from biology. And in return, the attempt to design better artificial vision systems may give us a fuller understanding of how we can see. When I was doing research in Cambridge in the late 60s, I got to know a brilliant young mathematician, David Marr, who believed that mathematics might help biologists to understand the brain. He realized that seeing was essentially a problem of interpreting the flat, two-dimensional image inside the eye in terms of the shapes, movements, colors, and distances of real objects out in space. He suggested that the brain might use algorithms, sets of rules, to compute those properties of the world from the image, and that those same algorithms could be expressed in computer programs. Sadly, David Marr died of leukemia at the age of only 35, but he's left a lasting impression on the new science of computer vision.
Perhaps the problem that David's best known for is his work on stereo vision. You have two eyes, And if you close and open those eyes in alternation, you get slightly different images. The slight differences between those two images enable you to reconstruct quite a lot of useful depth information, how things are arrayed in space. The key to stereo is to find some point, for example this point in the left image with the same point in the right image. It's very easy to state that. The problem is there's something of the order of 250,000 points in the left image and 250,000 points in the right image, and hey presto, if you try to match all points in the left to all points in the right, you're here for a week.
But animals don't have a week to see the world. A monkey on the move must recognize the distances, colors, and movements of objects, as well as their shapes, with every glance. Where is all that information analyzed? Semir Zeki at University College London believes that the answer lies in that huge unknown territory in front of the primary visual cortex. Here are other visual areas covering more than half of the cerebral hemispheres, and each containing its own picture of the visual field. The primary cortex at the back receives the signals from the eyes, but then sends it forward. In one of these areas, V4, Zeki's been recording from nerve cells which respond specifically to color. This cell doesn't care about the angle of a line, but only that it's red. To be sure a red object is always seen as red, whatever the color of the light falling on it, our V4 cells have to do a clever comparative analysis of everything in view.
The color that you see depends not only on what's coming from those red flowers, but on what's coming from the surround. And so, if you've got a dramatic change in the wavelength composition of the light coming from them, you're also going to have a dramatic change in the wavelength composition of light coming from the surrounding areas, and the brain compensates for the two. And you can see this, in fact, you hold this filter like that. Now this is a pretty strong blue filter. The reds remain red. There's very little change. There is some change, of course, but very little change in the color of the red flowers.
If this effect works for you on television, you're probably sitting in a fairly dark room. Otherwise, your V4 cells will compare the red flowers with the objects in your room and not with the other things in my garden. Nerve cells in your primary visual cortex can also respond to color, but they alone can't perform this trick of comparison. The secret of V4 must lie in the connections that it receives. Semir Zeki has mapped out how some of the different visual areas are connected, starting from the primary visual cortex, V1. In areas V2, V3, V4 and V5, cells are analyzing distance, contrast and movement, as well as edges and color. Special anatomical stains have helped Zeki trace the analysis of these various features through the areas. Nerve cells in different regions of the cortex can have very different functions, but the structure of those cells and the way they're connected look remarkably similar all over the cortex. There must be some kind of common plan, a set of basic building blocks consisting of small circuits of nerve cells, each performing a logical operation, rather like the chips in a computer. My hope now is that we can discover those building blocks. Here in Oxford, we've been looking at the shapes of nerve cells and the interconnections between them in thin slices of cerebral cortex under the microscope, rather in the way that an electrical engineer might investigate a single circuit board from a computer. Vision is one subject in which the physiology of the brain and the science of computers are working hand in hand. Psychologist Richard Gregory, who taught me when I was a student in Cambridge, also sees a growing link between the physiology and the psychology of visual perception.
And I think this is the immense achievement of physiology, that they're now asking much more exciting questions because you can begin to see ways in which they might be answered and need some being answered. So that physiology and psychology really come together, and the whole thing is enormously enriched simply, I think, by technology, by the techniques.
But do you think that just analysing how the retinal image is processed in the brain is really going to tell us everything about how we see the world?
No, I don't think so at all.
Well, what's missing?
Well, what's missing, I think, is, extracting meaning from signals. It's all very well having a bunch of action potentials getting into the cortex and then filters and analyzers and these things, but ultimately they have to relate it, don't they, to objects. If I'm seeing you there, a person I know well, I can read your expression, I know you're a person, I can see the thinking. There's a heck of a lot more going on than what I'm processing from my optic nerve.
How do we turn impulses into perceptions? An ingenious computer technique for analysing brain waves gives a clue.
Janet, now you're going to be looking at a checkerboard pattern repetitively flashed on this TV screen. I want you to keep your eyes focused on the center of the screen.
Okay.
Electrodes glued to the scalp pick up the tiny electrical signals. The computer turns them into a picture of the living brain at work. Jessie Salb, the inventor, is watching the brain process an image. The light from the screen flashes into her eyes, and the signals rush through her brain. Slowed down, we can watch vision as it happens, first at the back of the brain. About 0.3 of a second later, we see activity in the areas of the frontal lobe that are involved in planning, movement, and speech. Perception is recognition and the formulation of a plan for action. We transform shapes, lines, distances, and movements into objects, things we can recognize, name, and interact with. Somehow we know that this is a Dalmatian, and which way it's moving. Mortimer Mishkin has explored the pathways the brain uses for the analysis of a visual scene.
The striate cortex is simply the first station in the cerebral hemispheres to receive information from the retina. And it looks as though the striate cortex in the back part of the brain sends information forward along two different pathways. One headed to the top part of the brain, to a region that we call the parietal lobe, and another headed toward the bottom part of the brain, toward a region that we call the ventral part of the temporal lobe.
That higher northern pathway running towards the parietal lobe may tell us where things are in the visual field. It helps the jugglers to catch and throw. The lower southern pathway's function is to identify what things are, helping them to recognize faces, hands, and objects. Nowadays, it's common knowledge that the cerebral cortex is probably responsible for perception, thought, and consciousness. It's hard to believe that until the middle of the 17th century, no one thought that the substance of the brain had any important function at all. The person who first drew attention to the cerebral cortex was Thomas Willis, who studied medicine in Oxford and was the foremost physician of his day. After the restoration of Charles II in 1660, most of the great Oxford scientists moved to London to set up the Royal Society. But Willis stayed here, and he was rewarded with the professorship of natural philosophy. He dissected the bodies and the brains of executed criminals, but he also emphasized the continuity between animals and man. He saw that the cerebral hemispheres were very large in human beings, and in his great book, Cerebri Anatomy, he suggested that they were responsible for sensory perception, for memory, and for intelligence. Thomas Willis had an able young assistant, another great anatomist, but he was also a professor of astronomy. He helped to found the science of meteorology. He was a skilled microscopist. Isaac Newton called him the foremost geometer of his time. His name? Christopher Wren. He was a pretty good architect as well. This was his second major building, the Sheldonian Theatre, which he designed in 1663, the year that he drew the illustrations for Willis's famous book. The Sheldonian Theatre is modelled on a Roman theatre with an open roof. To give the illusion of Italy in rainy Britain, Wren commissioned Robert Streeter, court painter to Charles II, to paint sky and clouds on the ceiling. Through the visual deceit that is art, even angels become real, subjects for the computational power in the cerebral cortex. And the brain, it seems, has a special place for faces.
When a baby is a few hours old, it's important, isn't it, that it recognises a face, later on its mother specifically, but the fact that there's a human being close to it and so on. And then we read facial expressions. And I think also gestures, I mean, the way one's fingers move and so on. You can predict if somebody's about to sort of slosh one or hand one a sandwich, don't you think, by the way they move their hands. That's also important. Actually, I brought something along thinking we might get onto faces, which demonstrates rather nicely the enormously powerful assumptions that something is a face. What this is, it's simply, as you can see, a box, and it's got a couple of faces made of plaster of Paris. And you see, that is an okay face. It's actually Byron, as a matter of fact. And that's a hollow Byron. But it doesn't really look hollow. In other words, the nose here looks as if it's sticking out, when it isn't. I can actually put my hand inside it. And if I move it, you will see that they move in opposite directions. I don't think that's rather bizarre. The motion parallax is physically okay, but you get the appearance of depth the wrong way around on that one, and so the motion parallax generates the opposite motion. That one illusion is in fact generating another. But the real point of this that's so interesting is the enormously powerful effect of shapes here, which are typical face shapes, like the nose shape, the eye shape, the eye and so on, mouth shape here, which calls up, I think, the hypothesis, it is a face. The internal hypothesis in one's brain has the knowledge, the information, that people's noses stick out, not in. All one's friends' noses stick out, however peculiar they are. And that internal information in one's brain is actually throwing away or rejecting all sorts of data coming in from the eye, which is very good evidence that perception is not simply what is coming in from the eye.
For social animals, faces are very special. No wonder then that a specific region on that southerly pathway into the temporal lobe seems to be devoted to analysing faces. We're listening to impulses recorded from a single nerve cell in the temporal lobe of the monkey's brain. David Perrett wants to know what kind of image the cell responds to.
So what we're doing here is presenting different types of stimuli. Some of these are very complex and meaningful, such as the hand. Others are fairly arbitrary. But not all of these work. In fact, if you listen to the next slide, the one that's coming up now, then you can see that works.
Perrett finds that individual cells in the monkey's temporal lobe can respond selectively to faces, even human faces. To do that, they must be receiving information from thousands of other cells.
That's fairly convincing.
It's very surprising, David, to see a nerve cell in the brain responding to the sight of a face. How do you think those cells might get that property?
I think that's a complicated question. I mean, starting from the beginning, we already know that early on in the visual system, the presence of edges and of specific orientation is important. One can imagine a progression through more complex processes where combinations of edges, combinations of different parts of an object are analyzed and put together. I mean, we're seeing really the very tail end of this processing, the culmination of processing, where one object is being made explicit. The cells we look at do fire only to the presence of faces.
Do you think there's an area similar to this in the human brain?
Yes, I do. There's a good deal of evidence that specific disorders in face recognition can occur in humans. And these cases are quite bizarre and quite crippling. A patient may lose the ability to recognize even close friends, even their own spouse, or sometimes themselves in a mirror.
Several years ago, Paulette had a stroke.
Since then, she has been complaining mostly about the impossibility of recognizing faces and places. This is a very serious problem. And in her everyday life, Paulette constantly has the feeling she is living in a foreign place among strangers.
Sometimes people say hi to me, so I say hi to them. Other times I say hi to people I believe I know, and they say, who is she? What does she want? So I've been traumatized. And now I don't say hi to anybody, except when people call, hi poet, or when I recognize friends from their voices.
On regarde une autre série de photographies.
Quoi? What?
I'm looking for his name.
How old is he?
Over 70.
Over 70, right.
He has a little mustache.
Yes.
And inquisitive eyes with a mocking look.
Yes, perfect description. He was president of the Republic as well.
C'est le Général de Gaulle? Le Général de Gaulle.
Oh, Charles, I didn't recognize you.
Paulette can obviously see faces. She can describe them perfectly, but she can't translate those details into a flash of recognition. She suffers from prosopagnosia. The part of her brain that specializes in recognizing faces has been destroyed.
His face is familiar, but I can't put a name to it.
Well, who is he? Can you at least tell me what he does?
I think he is a singer.
Now Michel Poncet shows her a picture of himself.
Well, go ahead. Describe his face.
A little pimple on the side over there. In fact, 3 of them. I won't look any closer because he's got too many. He should go and see a skin doctor. To have his skin cleaned, because it's in bad shape. His eyes smile as well as his mouth.
Yes.
And his hair?
What about his hair?
It's quite thin.
Don't you think that's me? Don't you?
No.
How many compartments we have in our brains. She can tell everything about him, except who he is.
That's me.
That's you? It's not a recent picture then. I am mad at myself. I'm really mad. I don't recognize myself anymore. It gets on my nerves, that's the truth. It happens all the time that I hit my head whenever I make mistakes. I hit my head to put everything back in place.
Sad cases of brain damage, like that of Paulette, demonstrate so vividly that our perception of the world isn't the single, complete picture of reality that we feel it to be. Instead, it's a kind of patchwork of ideas. The shape, the color, and the movement of every individual object may be painted into my perception by different sets of nerve cells in different parts of my brain. As I look around Christopher Wren's Sheldonian Theatre, those visual areas in the southerly route through my cerebral cortex, stretching from the back down into the temporal lobe, are analyzing all those features of the scene, helping me to identify individual objects, to recognize the faces in the portraits, Christopher Wren himself, for example, up there, and to see the cherubs in that painting on the ceiling, which represents the triumph of science over ignorance. But the visual areas on the northerly route, up into the parietal lobe, may be more concerned with identifying where objects are and where I am in relation to the things around me. Damage to the parietal lobe, especially on the right side of the brain, can produce a bizarre kind of perceptual loss, a denial of the very existence of half of the world. Such brain damage causes a syndrome called neglect. When asked to copy a clock, a patient with this condition knew that all the numbers should be there, but simply couldn't perceive the left half. One patient asked to copy this, drew this, thinking his copy was a whole butterfly. When asked to copy a butterfly without a left wing, he drew it well enough, but again said that he'd drawn the whole insect. Now shown the left half alone, he drew only the body, saying it was missing only one wing, the right-hand one. In 1967, Anton Rederscheit, a world-famous artist living in New York, had a stroke which damaged the parietal lobe on the right side, the side that deals with the left half of the visual field. He too suffered from the syndrome called neglect. In particular, it affected the way that Rederscheit attended to things in the visual scene.
Attention is what focuses the nervous system on only a segment of the available information. That's why we need attention. There needs to be a mechanism for concentrating the focus of awareness on that which is important to that individual at that point in time, while holding the other sources of distractibility at bay.
Attention is complex. It involves many regions of the brain, but this area, near the back of the right hemisphere, a part of the parietal lobe, is crucial for attention to visual space. For Anton Rederscheit, the injury to his parietal lobe caused his change in perception.
He began drawing so far to the right that he was off the edge of the paper, so I had to put the brush on the sheet for him. And yet he was still attracted to the right. His first self-portraits were sketches of profiles. He only made partial portraits, an eye, half of a lip.
In addition to neglect for the left, there seems to me a magnetism for the right side of space. And some of these patients, as they lie in bed, will start to turn around towards the right side and really keep rolling towards the right side of the bed until they come up to the railing and just hold on to that, looking to the right side. It's as if, so to speak, they were trying to get back to the center of the universe where they should be. But now they have this strange situation where there's nothing on the left, and they keep trying to go to the right to put something on the left. But of course that's not very successful, because the problem is not with what's out there, the universe is there just as it always was, but with the representation in the brain where the bias really is.
Gradually, by himself, he began to control that force, which attracted him to the right. He drove toward the middle. He could see what was behind the face, and the portraits contained a vision they never had before. They weren't just portraits. They were something more, something which no longer had anything to do with reality, but with the picture itself. There was something behind the face. It was as if he was no longer painting simple portraits. He was creating. And when this final face was complete, he thought he had succeeded.
Rederscheit had succeeded, but only by struggling to invent the left half of everything he painted. Information from each side of the body goes to the opposite side of the brain, and many functions are performed half on one side, half on the other. But certain tasks are committed much more to one hemisphere, especially in human beings. The right hemisphere is specialized for spatial judgments, while the left can describe its perceptions in words. Normally, these two specialized halves work together as one.
I know the left hemisphere and right hemisphere now are working independent of each other, but you don't notice it. Now, you just kind of adapt to it. You don't have any feeling, it doesn't feel any different than it did before.
The corpus callosum, a huge bundle of fibers, connects the two halves of the brain. When it's damaged, in Joe's case through surgery to relieve epilepsy, then it almost seems that there are two separate people sharing a single head.
What we can do is play tricks by putting information into his disconnected, mute, non-talking right hemisphere and watch it produce behaviors. And out of that, we can really see that there is, in fact, a reason to believe that there's all kinds of complex processes going on outside of his conscious awareness of his left half brain. Joe, I'm going to show you some things. I just want you to tell me what you see. And here we go. You ready? Look right at the dot. Okay. Right. Okay, you ready? Look right at the dot.
Grapes.
Good. When Joe focuses on a point, everything to the right of the point goes to his left brain, the dominant hemisphere for language and speech. So we can see here that when we flash a word or a picture, Joe is easily able to name it.
See it.
Close your eyes and let your left hand do a little work here. Okay, what do you got there?
Pen.
Okay, very good. Now, when a word or a picture falls to the left of a fixation point, that information goes to his disconnected right half brain. And as we can see here, Joe is unable to name it. Joe is able to draw the picture with his left hand, the left hand getting its major control from the right half brain. What did you draw?
Okay.
What did you see?
Wheel. One side. I don't know where I saw the other.
So even though he can't name it, his left hand is able to draw out the picture of the stimulus of the picture or word that we presented to his right half brain. What did you see?
Hammer.
So just close your eyes and draw with your left hand. Just let it go. Nice, what's that?
Saw.
Yeah. What'd you see?
Hammer.
What'd you draw that for?
I don't know.
What Joe and patients like him, and there are many of them, teaches us is that the mind is made up of a constellation of independent, semi-independent agents, and that these agents, these processes can carry on a vast number of activities outside of our conscious awareness. Even though that goes on, there's some final stage or some final system, which I happen to think is in the left hemisphere, that pulls all of this information together into a theory. It has to generate a theory to explain all of these independent elements. And so, and that theory becomes our particular theory of ourself and of the world.
From impulses leaving the eyes to a theory of ourself and the world, we're beginning to learn how the cerebral cortex gives us our understanding. Francis Crick, famous for his contributions to molecular biology, is now fascinated with perception and with the relationship between brains and computers. If you damage one part of a computer, the whole thing usually goes wrong. Isn't it surprising that brain damage in human beings can produce such specific losses?
No, because we really do believe that brain isn't a general-purpose computing machine, and the different parts do different jobs, even though the parts interact to produce the final percept or the behavior and so on. The trouble with human damage is it's rather crude. It's not as confined to, say, to one area of the neocortex, and preferably on both sides. Now, occasionally you do get rare cases where there is rather better defined visual damage, and then you can get very interesting results. One is a lady in Germany, for example, who has damage in part of her visual system, and she can see perfectly well, except she can't see motion. So when she tries to pour out tea, she sees it as a gleaming column of liquid, but she doesn't actually see the tea rising, and so often it will overflow. She's frightened of motor cars because she can't see them moving, although they change position from time to time. There are other people who have damage in which they suddenly can't see colors anymore, but they see everything clearly in black and white. And all this is because there are different areas of the brain which specialize in handling different parts of the information.
So you think that's a way forward, to look at carefully defined clinical cases of people with brain damage?
Yes, but I think there must be 2 points. First of all, there must be selected cases where the damage is rather is rather small and preferably bilateral. And secondly, you must do as much as you can in detailed psychological testing, because if you do it rather crudely, you'll be activating a number of different systems and you won't be able to understand the result. And you must do it with some understanding of what's going on, or at least some guesswork, and the tasks that do that. So you must distinguish between a monkey being able to tell where something is, on the other hand, and whether it's novel. And if you don't do the test, you may mix them up. But I think in the long run, what you want to do is be able to do the same things on animals, because you should be able to do the
interfere with the system more delicately there than you can do in human beings. And this is largely the case for using animals for work in relation to the brain. And we hope that we shall have more tools which will give us, so we can knock out not really one little bit of an area, as we can do now, with certain chemicals going in and reversibly, but actually a limited subset of cell types in that particular area. So if we want to know what this cell type is doing in the visual cortex, by knocking it out and trying to get the animal telling us what it sees, we should be able to get some idea of its function. And I believe in the long run, I would go further than that. I don't think you can unscramble a complex system unless you can interfere with it repeatedly and delicately and preferably reversibly.
The dream of the 19th century neurologists to explore the entire continent of the cerebral hemispheres may well be completed within a few decades. But when the exploration's finished, will we really be any closer to understanding how it works? After all, we still don't even know how those nerve cells in the primary visual cortex respond selectively to lines and to edges. The cortex, like a computer, is essentially an instrument of connection. And to find out how it works, we must look at those billions of nerve cells and the thousands of nerve fibers that contact each one of them. The cerebral cortex is the key to our perception of the world, but it also holds the secrets of memory, thought, and of consciousness. It's the organ of understanding. Probably more than half of the area of this vast sheet of brain is consumed with the task of vision, and that alone is ample evidence of the immensity of the problem of understanding what we see. And the closer that we look at the rest of the cortex, the more we see that it too is divided into a number of processing areas for hearing, for touch, for movement, and for thought and for language too. The huge cerebral hemispheres of the human brain may well have evolved through the gradual addition of more and more of those modules of interconnected nerve cells, forming new dedicated areas, each extending a little further our understanding of the world. If any part of the brain alone is responsible for making the human mind, it's surely the cerebral cortex. To understand that organ of understanding will, in my opinion, be the most important step in our study of the mind machine.